1.5, which is all about modeling. And if you haven't noticed in your math classes yet, anytime a section is called modeling, it means you're probably dealing with some word problems. So section 1.5 is going to be a good number of word problems for you, but because you're so smart, I think you'll be able to do very well. So let's just start with this hotel here. We are given a table of values that says it's the height of the ceilings in a hotel from the ground level. Okay, so the lobby ceiling is 20 feet high from the ground. The first floor has 32 feet as its height. Second floor will be at 44, and so on, as you can see. I'm asking you to write a function that would give us the height of the ceiling in terms of its given floor. So that means our floor is going to be our x's, and our height then will be our y's. The independent variable is x, though dependent variable is y, and the height off the ground will depend on what floor number we are on. Okay, so a couple things to notice. The lobby is like 0, right? That's the 0th floor, so that's our beginning. So that could be thought of as like a y-intercept. And then we have first floor, second floor, third floor. So these are all increasing by 1, our x's. That's a good sign. And then we check out our y's. That's an increase of 12. From first to second floor is an increase of 12. And from second to third is an increase of 12. Except I wrote 13. Increase of 12. Okay? That's really important because that actually tells us our slope. This is a linear sort of relationship, and we can see that our slope is 12. And we talked about this here lobby being kind of like our y-intercept because it's when x is 0. So an equation could be y equals 12x, because it's our slope, plus 20. Okay, and this is if I use x as the floor number and y as the height above the ground. Okay, and it is important to tell people what variables that you are using and what they represent, because somebody else in class might not have wanted to use x and y like I did. They might use something else, and I need to know what they represent. So start by defining your variables somewhere in your problem so I can see what it is you're talking about at any given time. Okay? Now we have a follow-up question. Once we have that function, can we predict the height of the 20th floor? So 20 will be an x value because it's the floor number. So we want x, or y equals 12 times 20. We're just plugging 20 in for x. Plus 12. So we take our calculators, 12 plus 12 times 20, oops. And then we're going to add 20, not 12. And I think, if I did that correctly, I get 260. So 260, and height was in feet, so we should probably give our answer a label. So that would be the 20th floor would be 260 feet off the ground. Does that seem like a logical answer to you? That's a good thing to ask every single time, because sometimes we'll get, we'll make mistakes in our equation and we'll just get answers that are ridiculous sounding. So you want to make sure that it's logical. Okay, let's look at this. Here we have Julie, and Julie's heights have been recorded at various ages. So we have age 5, 6, 7, and 8. And there's a hint up there to find a pattern. Patterns are always a really good idea. So we can see that between age 5 and 6, she grew 2 inches, and another 2 inches the next year, and another 2 inches the second year, or another year. All right. So if we were just going to use the pattern, how tall would she be at age 11? Well, at 9, she would grow another 2 inches, so that would be 54. 10, she would grow another 2, so that would be 56. And 11 would be 58 inches. Now I know those look like fractions, I didn't mean them to be. Okay, just an extension of the table. So 58 inches is my prediction for Julie's height at age 11 if she keeps growing 2 inches a year. Now, can we turn this into a function? And a function is equation, really. I don't know how tall she was at age 0, so I don't really know the y-intercept, but I bet we could figure it out. I do know that +2, those 2 inches are pretty important. So that sounds like a slope. I'm going to use x for age and y for height. So what would we call her height kind of at birth? If I had to go if I only know age 5, and I had to really go to age 0. Let's go from 5 to 4 to 3 to 2 to 1 to 0. I would have to, instead of add 2, I'd have to subtract 2. So I have to subtract 2 1, 2, 3, 4, 5 times, as you had probably guessed. So if I have to subtract off 2 5 times, that's 10 inches. So her height at 0 was 36 inches. It's a pretty tall baby. 36 inches, 3 feet. Okay, so we have our function. Maybe it's a little unreasonable. Maybe. But it's the best we can do with what we have. All right? Under here, we got some questions. Now that we have the function, I want us to predict Julie's height now to age 19. So we're going to have y equals 2 times 19 plus 36. So 2 times 19 plus 36, 74 inches. Okay, and 74 inches is like just over 6 feet. It's like 6 feet 2 inches or something like that. Okay, not bad. Julie could be a very tall 19-year-old. It's possible. 6'2". Let's predict her age now at 35. So we do 2 times 35 plus 36. So we would get 106, I think. 2 times 35 plus 36. 106. Okay, 106 inches is 8 feet 10 inches. Okay, do we think Julie is 8 feet 10 inches tall at the age of 35? Do you think that is possible? Maybe. I would like to know if you think this model is reasonable for predicting Julie's height at any age. Could it have made sense at 19 at 6'2"? Yes. Does it make sense after that with an 8 foot 10 inch height at 35? Probably not. Do you know why? I would say it's because this is not a reasonable model. And I would say no, because this model that we came up with assumes that Julie's going to keep growing forever. Like, she never stops growing taller. And that's just not logical. So this might be a flawed model. It might be accurate for some years, but not forever and ever. Okay? And that can happen. Okay? So when you are approaching these application problems, you kind of have 3 helpful methods up here that will help you. If there's a formula that you know to use, go ahead, use the formula. Look for a pattern. Sometimes just drawing a picture will help. Okay? Some of these are very hard to visualize, but drawing pictures could help you out. All right? So let's see. We have Andrew and Jack who are going to go on a road trip. They're taking turns driving on a 400-mile road trip. Okay, so total of 400 miles. Andrew, I'm going to make Andrew orange here. Andrew drives for 3.2 hours at 60 miles per hour. And And Jack is going to take over after that 3.2 hours. He wants to drive 4 hours, but we have to figure out his average speed. Okay? So, I like to set up these things. When we're talking about distance, rate, and time, there's a formula for relating the distance, the rate, and the time. Does anybody remember what that happens to be? Okay? Distance is equal to the rate times the time. Okay? So if Andrew, I like to record what I know. Okay? Andrew is driving for 3.2 hours. That's a time, so 3.2 hours there. And he's going to drive 60 miles per hour, so that's a rate. All right, and if I want to know what distance he drove, it's going to be 60 times 3.2. So 60 times 3.2 on our calculators gives us 192 miles. Okay, now we know very little about Jack. That's where we're trying to figure stuff out. Okay, we don't know what rate he's going to go. His time is going to be 4 hours because it was given to us there. Okay, and he's going to drive the rest of the distance. Well, if they're starting here and they're going 600 miles, and Andrew stops here at 192, how many miles does Jack get to drive? Did you figure that out? He gets to drive 408 miles. Okay, I did that by taking 600 and subtracting 192. So Jack is going to drive 408 miles. Now this is my unknown right here for Jack. I need to figure out what his rate is. So remember up here, distance is equal to rate times time. So 408 distance is equal to the rate, we don't know, so we could call it R for now, times 4. Okay, divide both sides by 4, and you get R is equal to, let me calculate, 102. 102 miles per hour. Oh my goodness, Jack is going to get a speeding ticket or cause an accident or something. He should probably not drive that fast. Okay? But mathematically, if they want this to happen, he'd have to drive 102. Okay? Now this last one is a bit of a challenge question. I would like you to maybe try this one on your own and think about what's going on, and tomorrow in class we could certainly talk about this one, but I think I'd like you to try it on your own, see how you feel about it. Okay, let's talk about this tomorrow. Good luck.